Exponential modelling. The fact that y is equal to e to the x is a self-differential, so that y equals e to the x implies that dy dx is e to the x, makes it very good for modelling situations where growth or decay of the amount of a substance is dependent on the amount of a substance present. Examples are things like population growth, although there we're thinking of substances, perhaps people, and the decay of radioactive isotopes. As an example, consider a medication and the levels of it in the bloodstream. We will consider that the rate of decrease is proportional to the amount of medication in the bloodstream at any time. Suppose at one time there is 100 milligrams and that the decrease is 4% per minute. This is going to have the form dA dt is equal to negative Ka, where K is a positive constant. So the rate of change with respect to time is going to overall be negative and proportional to the amount of the medication in the bloodstream. That's why we've got the A here. In this case, 4% per minute, the K would be 0.04. So we get dA dt is negative 0.04a. The rate of change is minus 4% of the amount present, if you like. The solution to this equation, in this particular case, where we start with 100, is A is equal to 100 e to the negative 0.04t. And we get the 100 here because when t is 0, the exponential would be e to the 0, which is 1. And we know when t is 0, there's 100, which is why I said in this particular case. If we differentiate this, then we get 100 e to the negative 0.04t times the negative 0.04. We've established this earlier on, and we said it was an application of the chain rule. So, we multiply these things, and we get that dA dt is equal to negative 0.04a. And that's how we can tell that that's a solution, because when we actually do the differential, it gives us the equation. So, we have A is 100 e to the negative 0.04t. We can graph that. We know what exponential graphs look like, but of course this one's not going to have any portion to the left of the axis because t starts at 0. And we know that when t is 0 it's 100, and then we get exponential decay, and so the t-axis here will be an asymptote. As an example, a second example, consider bacterial growth. Suppose that initially there are 10,000 individual bacteria, and the number of bacteria increases by 10% each hour. dN dt is equal to Kn. K is a positive constant, and this time since it's increasing, it's Kn. So dN dt is 0.1n because of the 10%. This has a solution. N is equal to 10,000 e to the 0.1t. And we'd get that exactly the same way as we described with the previous example. The 10,000 comes from, that's the value, when t is equal to 0. So what does that look like? Well, we know what an exponential curve looks like, but once again, of course, it's going to start from the intercept here because t starts at 0.